Oh, you notice I didn't swear there, right? I did not swear. Oh, probably felt like doing it. There. I want to go back to this page. The integral test. The integral test says essentially this. Suppose you have a series. If the integral from 1 to infinity, if this integral, it's called an indefinite integral, converges, then your series also converges. And if this guy diverges, then so does your series. Now, I'm going to do, I'm not sure what the phrase is, but do as I say, not as I do. These questions have two things that have to be true before you can do it. The first thing is that that guy has to be positive, right? And the second thing is that that guy, right, the formula for n has to be increasing. I am, for the most part, not going to do those two steps. They just take up a lot of time. And I want to get to the third step, which is testing if it converges or not. Because I'm not doing it doesn't mean that you shouldn't. Because if you get, and you will get a test question from this section on the integral test, you have to prove that it is positive. Well, that's not much of a proof, right enough, but you do have to prove it's increasing, and you're going to be proving it's increasing by showing me that its derivative is negative, right? So most questions I will not do that. I will go straight into this bit. But let's do our first version, question 1. And it's going to be that guy. And if you prefer, it's the same thing as that guy, right? So first thing I should do is I should take this fella here and prove that it is definitely positive. Now, when we're talking about this positive, right, thing, we're only talking about n, you know, being the numbers like 1, 2, and 3, so on, right? Would you agree that 1 over x to the 4 is always going to be positive? Right. So I'm really just stating it because there's not really any math I can think of that would be enough to prove that. Now, the second bit does require math, right? You differentiate. Multiply by the power and reduce the power by 1. And I'm going to call the derivative that guy. Now, we are only interested in n, or in this case, it's now going to be called x. Aren't we only interested in x's being numbers like 1, 2, 3, and 4, and so on, right? Now, all I need to do then is prove that this is negative. And here's my proof. Would you agree that -4 is always negative? Right, the number -4 is negative. Would you also agree that x to the power of 5 is positive for every value of x greater than or equal to 1? So those little plus and minus are my notation for the top is negative and the bottom is positive. What do you get if you take a fraction that has a negative thing on the top and a positive thing on the bottom? What can you tell me about that fraction?
The entire thing is negative.
And isn't a derivative negative means that we have now proved that it's decreasing? Are you happy about how I proved that it was decreasing? Proving it's positive is something you don't really need to spend a lot of time in, because it clearly will be or it would be, right? There won't be anything in between. So it's decreasing. That bit, the 1 and the 2, is going to kind of disappear from now on. So I'm not going to do 1 and 2 for any of the later questions, but you will assume that I did do step 1 and 2, right? You're just, you know, I can do more. I can do twice as many questions because I'm missing that out. But back to this fella, we now have to find this integral. And if I can find this integral and it's equal to a number, then the original series converges. And if I can find this and I find out it's infinite, then the original series diverges. These guys become, I'm only going to use t because that's the one I'm used to. Are we comfortable about how the infinite integral becomes a limit? How this mathematically becomes this? You comfortable with what I did? So what we now have is the limit as t tends to infinity. Right. This fella here, although he's kind of weird looking, is only just a power rule. So you add 1 to the power and you divide by the new power and you evaluate it at 1 and at t. To make life a little bit easier to deal with, I am going to rewrite this guy like that. Now plug in t, you get that guy. Take away this guy with 1. If you take away a negative a third, can I skip a line of working? Are you comfortable about that being a +3 at the end? Take away -1/3 times 1 cubed. Take away -1/3, add 1/3. You comfortable about that? Couple of lines kind of done in my head. Right. Now, in a question like this, wouldn't the simplest method for finding the limit be the brute force method? Right, just plug t as infinite. So what do I get? I get -1 over, well, basically infinity. Would you agree 3 times infinity squared is still infinity? Plus a third. So the answer ends up being 1/3. So this converges. Technically it converges to 1/3, but it converges. And I've run out of room, so I'm going to squeeze it in here. So doesn't that now mean that this fella converges? So we found out the answer. Most of the questions, you just have 2 choices. Hit a dot that says converge or hit a dot that says diverge. But can you see how much work is involved in getting to that stage? Now, I'm pretty sure I've mentioned it, but I want to mention it again. This integral converges to a third. So the area under this curve is a third. It doesn't mean that this thing converges to a third. It just means that this thing converges. And the reason for that is that you've got a smooth curve, but you're filling in little rectangles. And aren't rectangles not going to have the same areas under the curve? Right. So what you can say for sure is that it converges. You cannot say what it converges to. It might converge to something close to a third, but it might converge to 4. You know, if all the little rectangles were underneath the shape, couldn't it converge to a quarter? Right. So make no assumption of what the number is. Just say it converges and call it good. Let's try our next set. Let's do this fella. He's a bit like question 2. And the only piece, essentially, I'm doing is step 3. Can you trust me that that particular guy does decrease and he is positive? Right, so 1 and 2 are done. So this is going to be the limit as t tends to infinity of 1 over t, 2 lots of 3x minus 1. So we are going to be testing how good you are at remembering Calc 2. I'm going to integrate 2 over 3x minus 1. What kind of function do you get? You don't need to tell me the details, but just the big picture. What kind of function do you get when you integrate those kind of fractions? What's its main feature? What's it got in it?
Natural log.
It's got a natural log. Now that 2 goes there, and you get a natural log. So that's a good start, right? Wait a minute, there's a 3x minus 1 here, isn't there? How do you compensate for the 3x minus 1? Because that answer's about 80% right, but it's got one major piece missing, and then it's 100% right.
You multiply by 3 or 1/3.
Yeah, multiply by 1/3 or divide by 3. In other words, stick a 3 in the bottom. Are we cool with that now? Right. Now I'm going to kind of move over here because I think I need more room. And I'm going to have 2/3 the natural log, plug in t, 3t minus 1, subtract 2/3 the natural log of 2. Quite a lot of these, not all of them, but quite a lot of these guys that we're going to do are just going to be done by brute force, right? So that's at least something, right? Well, if you plug infinity in here, would you agree 3 infinities take away 1 is infinity? So what you've got is 2/3 the natural log of infinity, take away 2/3 log 2. What is the natural log of infinity? What number is it? Or what is it? Maybe it's not a number. Natural log of infinity.
It's infinite.
Right, so won't that be infinity? And isn't infinity take away a number still infinite? And so it diverges. Which means that this guy diverges.
Is this a method for proving that the harmonic series diverges?
Interesting question. Let's
Because
find out.
that's a harmonic series, and that's just a, I think at least.
Right, that's the harmonic series, right? If you write that down, plug in 1, plug in 2, plug in 3, plug in 4. Do you see that's what the harmonic series looks like? Let's do the integral test on it. Will's thinking, I wonder if that's a proof that the harmonic series diverges, because you said it did, but let's prove it. And can you trust me it's positive and decreasing? I think that's pretty straightforward. So the integral from 1 to infinity of 1 over x dx, well, that's going to be the limit as t tends to infinity of 1 over t, right, 1 to t I should say, that guy. That's going to be the limit as t tends to infinity of the natural log of x evaluated at 1 and at t. And that's going to be the limit as t tends to infinity of the natural log of t, take away the natural log of 1. Now, if you do brute force on that, it becomes the natural log of infinity, take away 0. Isn't the natural log of 1 just 0? And the natural log of infinity is infinity. So that means it diverges. Which means we have now proved that the harmonic series diverges. And by analogy, couldn't I prove all the family versions of the harmonic? You know, like the 1 over 2n and the 1 over 2n plus 1 and all the other guys, they also diverge. And I can prove it using the integral test. Hey, so we've chopped off one of our guys that I just said, trust me. And now we've proved it. They're not kind of cool. That we actually have a formal way of saying something that we kind of knew was true, but proving it was a little bit different. So far, so good. Right. Now, Next one, kind of moving up the food chain. The ones that we've done so far have been reasonably straightforward. Here is our first fella. That one. So I'm going to tell you the first bit is true, right? It's positive and the thing is decreasing. But I'm going to rewrite it a little bit differently. I'm going to rewrite it like that. Are you happy that this is the same thing as that? Okay. Now, you can certainly keep it that way. It's going to work perfectly fine. So if you don't see any benefit to doing that, that's fine. But do you get at least a feeling that that bottom is really big compared to the top? So my gut feeling is that this is going to converge, right? Let's see if it does. When I wrote it like that, it's hard to tell what the heck's going on. When I write it like this, I get a better feeling for it. That's the only reason I did that. Oh, what technique from Calc 2 would you use to integrate this guy?
Integrated by parts.
It wouldn't work because I think I'm just doing it in my head. Yeah, it ends up being uglier once you do the f-g bit. But x e to the x, for instance, x e to the negative x, something that looked like that, that would have been an integration by parts. So it's not a bad idea, right? I mean, in some circumstances that would work perfectly fine, but not this circumstance.
Isn't it a U sub?
It is. And who is the U sub going to be?
Is it x squared? Or
Oh, so if it's not x squared, who will it be?
e to the negative?
No.
Oh darn!
Is
Sorry.
it negative x to the cube?
Yeah.
Yeah, that's it. That's what you were
That's it,
trying
okay.
to spell, but I confused you by saying no all the time and disturbing you. Right. You can do negative x cubed if you like. I'm just going to do x cubed because I figure out if I keep away from negatives, I'll probably screw up less. That's the only reason. So I try to keep away from negatives because I'm careless. So you differentiate with respect to x. You do the crossover. And then you isolate the dx. I'm just curious. If you got me, I know that's how I teach it. So I know that that's how you would probably write it down. Does anybody, because you used a different professor, do you do the U sub in a different way?
We had to kind of guess that. Not really guess, but just know that it did that at the very end.
Ah, so there wasn't a process, you just kind of knew it because you did so many?
No, there was no process. He just said the derivatives of this is that, and you had to figure it out. It was kind of hard. So this is easier.
Okay, that's cool. I should get more money then because I'm teaching it an easier way, shouldn't I? So when you say my boss, you say, you know, Professor Robertson, the guy that tells all the good jokes, can he get an extra 10%? You do that for me, Christian?
Absolutely.
I don't know. I think there was a bit of insincerity in that, but never mind. Here goes. I don't like putting the limits of integration with U subs because technically they're not 1 and 2 anymore. They get changed and I'm not going to do the change. So I have an x squared, I have an e. Now I'll take care of that guy, minus u. And the dx becomes a 1 over 3x squared, and I have a dx. And if you do it correctly, or at least if it's a nice question, do you see that you end up with quite a pretty integral, right? Something that you can integrate without too much trouble. Okay, I know it's got that minus unit, but you know, this question is going to have a negative somewhere, so you got to live with that. Okay, if you integrate this fella, you do get that, but you also get something else. What's missing?
Negative.
Are you happy about where that extra negative came from? It came from this negative here. You're comfortable where that negative here came from, right? You know, if that was 2, you wouldn't have a half. If that was negative 2, you wouldn't have negative a half, right? It comes from that. Okay, continuing, we now have the limit as t tends to infinity, negative 1/3 e to the negative x cubed, right? Because I'm replacing my u back in. And now I can put in the limits of integration. So it's roughly about here that they come back, the 1 to t. That's going to be the limit as t tends to infinity. Right, you plug in t, you get this fella. And if you plug in 1, this guy is e to the negative 1, this guy is negative 1/3, but you're taking it away. So I can save 1 line of working. Are you happy about that 1/3 e to the negative 1 and why it's a plus? Right, I'm taking away a negative, so that's a plus. And 1 cubed gets me 1, so negative 1 cubed, right? That's it. Now, I am not going to brute force this right now, because if I did, I might make a mistake. If I said to you, what is e to the negative infinity? There's a 50-50 chance you'll guess the wrong direction. So I'm going to put this in. Not everybody feels that this is necessary, but I'm going to call this guy that guy. So now I'll plug in infinity and see what we get. Negative 1 over 3. Okay. Would you agree that e to the power of infinity cubed is infinity? E to the power of infinity cubed is infinity. Okay. Isn't 1 over infinity 0? So minus 1 over 0 is still 0. So what do you get is a number. So it converges. Feel good about that? That some of the things I did, because that's the way my brain works. You may choose not to do some of these things. As long as the math is correct and the conclusion, of course, would be correct, you're fine. Some people, for instance, don't see a great need for taking this and writing that down. Any questions so far? Does today feel like deja vu and you're in Calc 2 again? Isn't about 90% of what I'm doing exactly what you would have done in Calc 2? We just got a little different reason for wanting to do it. I'm going to show you a lovely little shortcut. It's called the P-series. In fact, I guess if I'm calling it correct, it's going to be called the P-series test. Each one of these is an example of the P-series. The P series is any series that's typically written as 1 over a power of n. It could be 1 over n squared, 1 over n, 1 over n to the 0.9, 1 over n to the power of any number you like, okay? That is called a P series. This fella is called a P series, P equals 2. This guy is called a P series, P equals 1. And this guy is called a P series, P equals 0.9. Are we comfortable about the name and the terminology for doing it? So if I said to you, I have a P series and P equals 3, right? If I said I have a P series and P equals 3, are you comfortable in realizing that I've just told you this guy? Okay, now what's special about P series is that you can tell if they're going to converge or diverge very easily. So here is the P series test. If you have a P series, 1 over n to the power of p, right? That's the generic P series, right? That's all of them, right? 1 over n to the power of p. If p is greater than 1, the series converges. And if p, right, the power p, is less than or equal to 1, it diverges. Can you see how easy solving P series converge, diverge problems are? Isn't it just a matter of finding out the power of P and then using the test? So, will this one converge? The top one. I see nods, that's good. But anybody want to be brave enough and say yes or no? Does this converge?
Yes, it converges.
Yes. Isn't its p-value 2 bigger than 1? Converges. Oh, you remember this guy, the harmonic series? P less than or equal to 1? Yep, it diverges. Okay, what about that one? 1 over n to the power of 0.9. Converges or diverges?
Diverges.
Diverges. Isn't the p-value less than or equal to 1? Yeah, 0.9 is less than or equal to 1. What about p equals 3, that one?
Converges.
Can you see that you do not need the integral test for those P series? Isn't that going to be a lot less work because of that?
Just
Yes.
does that only work when the numerator is 1?
Very good question. You are thinking the right way you should. Her question was, does this only work when the top is 1? And the good news is, no, it also works when the top number's 10 or 2 or a half or 42. Now, the argument for why it works is pretty straightforward. Can you imagine you took, for instance, this guy? You are allowed to bring out constants when you do sigma notation. Does it make sense that this guy is just 10 times that guy? So if this guy converges, won't that one converge? And if this one diverges, so that one. So you can do it for even this fella. Because won't that guy be that guy? And then you would say P equals 1. And then you'd be able to say diverges with almost no algebra or anything really that major to do. Do we like the P series test? Because P-series test means I don't need to integrate anything. That's pretty cool. Any questions about that? Okay, so let's give you some hard ones to do. All P-series, even if they don't look like it. Here's your first one. This is basically a version of question 5. That is a P-series. I know it looks weird, but it is a P-series. First thing you need to tell me, which P-series is it? What's its p-value?
Square root of 2.
Wait a minute, isn't that bigger than 1? So answer, converges. Do you see how easy your working is going to be in a test for that one? Do you really want to integrate 1 over x to the power of square root of 2? Do you really want to do the integral? No, nobody wants to do the integral test, me included. So thank goodness I don't need them. How about this one? And be careful, because this is a kind of tricky question. It is a P-series. But if you're going to do a P-series, sometimes you have to do a little bit of surgery. Are you happy that this is equivalent to that? Now, when I write it this way, can you see that the p-value is a rather weird looking decimal? Agreed? But isn't it also a weird looking decimal that's less than 1? So what? Converge or diverge?
Diverges.
And we are finished. P-series is our friend, doesn't it? It at least reduces our workload. Question 7 is giving me a series written in a way that makes my life much more difficult. Before I even decide converging or diverging, we need to figure out what the formula for this darn thing is. But thankfully, it's not that difficult a formula. Can you see the formula for this fella?
Isn't it 1 over n squared?
Okay. Can you now see a P-series? Can you also tell it converges? How about this fella? Much more difficult this time. I know you'd call that too, but we leave it in that form. Okay, so the first term is that, the second term is that, the third term is that, the fourth term is that. Try and think what the nth term would be. There is a distinct pattern, 1 over something.
One over n to the square root of n.
Great. Then we have to kind of tweak it. Isn't n times the square root of n the same thing as n to the 3/2? Do you see why I needed to tweak it? If I left it like that, it's not obvious it's a P-series, and it's even less obvious what p-value it's got. Would you agree when you convert it to this? Is that going to converge then? Yeah. Okay. Are we cool? Any questions about that? Do you see algebra is your friend? You know, patterns are your friend.
I have a question of, would this work for telescoping series if there was a P series inside of that?
Oh, say that again, Victoria.
Oh yeah, so if there was a telescoping series and there
Mhm.
was a P series inside of that, would this test work for that?
Trying to think, you know, something like maybe a telescoping series that looked like that, for instance. Is that the kind of thing you're thinking about?
Yeah, would it make our life easier if we just did the P series on one of that on a test? Or is this that not possible?
I've never actually been given this question, and I like it because my brain, so I guess I know what I look like, but I probably look very strange when I'm deep in thought. I can't see anything wrong with your logic because essentially, couldn't you split it into that guy converges, that guy converges, and the logic says that if you're made up of two things that converge, shouldn't the answer converge? And so the answer to that is yes, that would work. Now you're not going to like the next answer. Still don't do it. Because if I give you a question like that, it's because I want to see, do you know how to do the telescoping series? And, you know, in this case, the P series trick that you just mentioned was really cool. And I don't want you to ding it because it is a very cool way of looking at it, just not a way I thought about looking at it. How would I make sure? I would put in the question that it was a telescoping series. If I say that, you got to do it that way. If I just give you a series, any math method that you know that's valid is going to be acceptable. How about that? Sound like a plan?
Yeah, it does. Thank you.
Okay, that's a cool way of thinking it. Never thought of that. Wonder why. Okay, I'm just doing a quick check. Right, that was a little subgroup, right? We started with the integral test, and then we kind of moved into these things called P series, right? And we did quite a few of them. And now we're going to go back to questions that involve maybe P series, maybe not. And it actually butts very well into what Victoria was doing. Now, this is definitely not a telescoping series. Would you agree? They'd have to have a minus and it would look quite different, right? But I'm going to see if I can use the technique of P series on this guy. So the first thing I'm going to do, which is allowed mathematically, would it seem reasonable that you could break this into two separate series? Would you think algebraically that should be allowed? Because it is allowed, but does it make sense that you could do it? So you're with me so far, right? Now, this guy here is a P series, but I have to figure out what P series he is. Now, I guess the square root, isn't that a half power? And you have a half power on the top and 2 powers on the bottom. Does it make sense that it simplifies down to what I have now got? Are you happy with the algebra that I did to convert this into two P series? Right. When you do P series, you want, well, you can get away with 2 on the top, right? We talked about that earlier in mod, don't we, right? You can have 10 and 2 and it's okay, right? But don't we need to have just powers on the bottom, right? So that's why we had to do this work. Would you agree that this is a P series 3 halves and this is a P series and it's 2? Does this first one converge? Yeah, bigger than 1. Does this converge? What do you think the logic is that if you've got a thing that's made up of 2 pieces, both of which converges, what's the logic of the entire thing then? Shouldn't it also converge? That makes sense. So this guy converges, plus this guy converges. Conclusion, the whole series converges. Would you agree the math logic of that is pretty understandable. It kind of makes sense that that would be true. Now, without going into the details, imagine I had this same situation, but the following combinations happened, because it can happen. The first one was a converge, and instead of a plus, it was a minus. So it's going to be something that converges takes away something that also converges. So imagine that question with a minus there. Would the overall series converge in that case? Yeah. Something converges. Take away something else that converges. How about the first one diverges and the second one converges? What would be your conclusion about the overall series, right? The thing that we started with. If one piece of it diverged and the other piece converged.
It would be divergent.
Yeah. Would you agree infinity plus 5 doesn't help it? It's still infinite. That's kind of the argument. For that same reason then, wouldn't a diverge plus another thing that diverges, wouldn't that just be even more diverging? Be careful with this last one. The first piece diverges, take away the second piece diverges. A bit like infinity, take away infinity, but be very careful. What, if any, conclusion can you come to if that happened?
It would still be divergent.
Nope. I understand why you might say that. Oh, it converges to 0. Nope, but I can understand why you might have said that. Oh, it just converges then. Nope, I understand why you might say that. The answer is, we don't know. The fancy word for that is inconclusive. And the reason for that is that although this might be infinity and that might be infinity, couldn't one of them be a bigger infinity than the other, a less infinity than the other, or about the same kind of infinity? That would mean essentially that the technique that we used was the wrong technique, right? We split them apart, we found some p-series, but darn it, no good, right? So maybe we should have done the integral test after all, right? Because there are going to be some questions that look to you superficially, oh, it's going to be one of those break them apart p-series tricks, and it ends up not being, right? And so you have to be aware of that and, you know, and tackle it a different way. Right? And here is a question that might look like, what's the time like? Oh, last one for today. That might look like it's a p-series. The only thing that wastes it is that +4. If I took that +4 away, would you agree this thing converges as a p-series? That +4, all bets are off. We're now back to integral test, right? So it's not like, oh, you only done a couple, don't worry about it. No, they're back with a vengeance, right? We're going to be doing a lot of these guys. So that means I'm going to be finding the integral from 1 to t of this guy. Okay. What is the derivative? What is the integral of 2 over x squared plus 4? Now that one is going to test you. Would you agree it's an inverse tan? Anybody want to have a guess at what the x squared plus 4 gets you? X plus something. You may have to go and look at standard integrals in a bit, since we're running short of time. Can I tell you it's x plus 2? If it was x squared plus 9, it'd be x plus 3, and so on. Now, there's a 2 there. There's also a 2 that cancels out with it. So that's what it ends up being. And you're going to have to check that out yourself because we're running short of time. So what do I have? I have the limit as t tends to infinity of the inverse tan of t plus 2 take away the inverse tan of 3. And then you plug in infinities. And I can understand why you might make the following mistake. Oh, the inverse tan of infinity is infinite or it's divergent or something, so the series diverges. That's not actually the case. The inverse tan of infinity is in fact a number. If you sketch the inverse tan function, it looks like that.
Pi over 2.
Yes. So what you've actually got is that guy, which is a number, so it converges. That series actually converges. It was an integral test with a really ugly inverse tan function that you probably want to look up. But remember, when you do a test, you can have any tables, formula sheets, whatever you want, right? So you